Welcome back, everyone. So let's continue. I think it's recording. Good. I still want to tell you about the implications of Goldstone's theorem. In fact, one of the biggest and most important implications is another theorem, which we'll call Mermin-Wagner. And that's what we'll talk about. But before we go there, were there any questions left about the first part? One thing that a couple of you asked me about, it's maybe good to point out, is is about the Fourier transform. Right? If you start in a harmonic chain where you start at position 1, 2, 3, 4, and so on, up to n, right? Then of course position only comes in discrete amounts. It's just a number. If you now Fourier transform this, we also assume periodic boundary conditions. If you then Fourier transform it, you will find that k is also a discrete number and also periodic. Right? And it goes from minus pi over a to minus pi over a plus 2 pi over na. So you see, in K space also everything is periodic and discrete. If in real space everything is periodic and discrete. Right, the periodicity in real space implies discreteness in K space. The discreteness in real space implies periodicity in K space. You see this quite easily from the definition of the Fourier transform. But what it means is that, for example, for K, I don't have to draw, if I draw this dispersion, omega as a function of k, right? I just drew it like this without labeling it. Really, I should say this is 0, and this is pi over a. And I'm not drawing anything beyond pi over a, because then it will just be periodic. Right? It just repeats everything that happens in the first Browne zone. See, maybe if I draw the full thing, this goes to minus pi over a. This thing is known as the first Browne zone. You guys remember the Browne zone from solid state physics? If not, then just take it as a definition now. It's the bit around k is 0, which afterwards starts repeating. And right, so the other thing is the discreteness. So really this comes in packets, or there's only some momenta that can be excited. And these are separated by 2 pi over na. And of course, when n is really large, which is the only situation we're ever interested in, the separation between these things becomes really small, and you might as well think of it as a continuous line. Because there's a pi in the definition of k, it also means that this exponent of k times ja, right, the a cancels the 1 over a in the k, and then there's something with pi, so that you see that, that actually this is an exponent of something times pi times some number, which is the reason that it starts cancelling each other if you go around the complex plane, like I mentioned before. And so if you were missing the pi, here it is, in the definition of k. Is this okay for everyone? Okay, so then, oh, yes?
Yes, so in this whole analysis, we've assumed that momentum and position are both observable.
No, not at all.
So that was actually, how do you meditate that? You have to choose one, right? And then the other becomes more uncertain.
But you don't choose it for any particle at all. So the question is, are momentum and position now both observables? So J and K in all of this are labels on my operators. Right? X is the actual operator. So X of J measures the position of atom number J. But J is just a name. No, instead of calling it J as 1, 2, 3, I could as well call them Alice, Bob, Charlie, and so on. Doesn't matter, right? It's just a name, a label. Of course, it's useful to give it actual distances, because then pi over the distance is the momentum. But what it means is that you can create a particle either completely localized by creating it like this, right, in a localized state, or you can create a completely delocalized particle with a fixed momentum, k, or anything in between by making superpositions. But neither of these operators create something that has both position and momentum.
We did exploit both P and X to be Hermitian in the Fourier transform and diagonalize the Hamiltonian.
Sure, P and X are both Hermitian operators. They're both observable.
Takes care of it.
but the fact that they are observable doesn't tell you that you will be in an eigenstate of them, right?
Okay, yeah.
That's the usual Heisenberg uncertainty principle. Any other questions about the stuff before the break? Yes?
So is the disclosure equation valid for k is equal to 0?
Good, it's not. So everything we did breaks down when k equals to 0. And in fact, you noticed it as well, right? In fact, we already knew this because we said it yesterday.
That the collective behavior.
Exactly. At k equals 0, you actually only have this collective behavior. And if you go back to the Fourier transform, you'll see actually the prefactor in terms of the x operators is 0 for k equals 0. So all we have left is the p operators. And the sum over p operators is just the total momentum. So at k equals 0, actually there's only the total momentum. Of course, this makes my hand-waving argument about Goldstone's theorem also a bit suspect. Okay. But you can read even more hand-waving in the lecture notes if you want. And if you want the proper definition, then read the fine print. Everybody okay then with Goldstone's theorem? Good. So then let's go on. Because when we did this whole derivation, right, we started with the Hamiltonian for a harmonic crystal like this, or a harmonic chain really. And we found that in this harmonic chain, things can move, can vibrate. But then you can ask. Sorry.
I have one question.
Yes.
Because we talked about these low energy excitations and the individual vibrations of the
Yeah.
atoms, but the atoms, you shouldn't visualize it as moving in time because they're stationary.
Yeah.
So, what is a good way to think about this?
Good.
I mean,
So when you you saw that the Hamiltonian was really the sum of harmonic oscillators. Right?
yeah,
So in their ground state, all of these harmonic oscillators are Gaussian wave packets.
yeah,
Which means that you should think of a single atom here. Oh, oops. A single atom here, really. You can draw it. Okay, this is a horrible thing. I will only do this once.
Yeah.
Because very soon we will go to many particle wave functions and you cannot make these drawings anymore.
yeah, yeah.
But for now it's okay. So if you draw the wave function of this one atom, right, it's a Gaussian wave packet and it looks like this. If you excite it, you go to the first excited state and it starts looking like this. Oh, that's the second excited state. Anyway. Right, so it spreads out. Let's be proper and make the first excited state, sorry. That looks like that. So it goes away to its rest point if you want.
Yeah.
Right, and it doesn't quite oscillate, but it's further away. And
Yeah,
spreads out.
so could you like say that it gets less localized?
Yeah, absolutely. Just like you do in the normal harmonic oscillator for one particle. Right, there is really no particle bouncing back and forth in harmonic oscillator, it's just a wave packet that's present. Yes?
Is the implication of Goldstone's theorem that nothing is ever not excited?
No, not at all. No, good. So you have to remember these are bosons. Right? And good. So if this is the dispersion relation of my bosons, then what is the ground state? The state with the least possible energy.
Zero.
Yeah, it's where you don't excite any of these bosons. So none of these particles
But
exist.
spontaneously you still get excited, right?
By what?
Because that's the implication of Goldstone's theorem. Right?
Oh, good. You mean because it has zero energy?
Yeah.
Good. Yes. So that comes back to your point. So all of these states exist, except at this point here, at 0, really doesn't exist. Because the K0 part is really this collective response, right, which we talked about yesterday, which is just the total center of mass momentum, if you want. So kinetic energy of the total thing. So as long as that total kinetic energy is 0, you cannot spontaneously excite anything. There really is nothing that happens exactly at 0. Goldstone's theorem, in fact, says nothing about exactly K equals 0. It says only that you approach 0 energy as you approach K equals 0. But it says nothing about what happens when you get there. In fact, it's a singular limit. Of the same kind of singular limits that we had yesterday. Okay. Everybody okay then? Okay, so then let's go on. So what we learned is that we have a chain of atoms, and these atoms can vibrate a little bit, or spread out their wave packets. So you might wonder, in the ground state, how far do these atoms spread? Right, that's a good thing to ask. I mean, you want to understand what this material looks like, maybe this chair, and this is something I could easily measure, right? I take a powerful microscope, I look at it, and I want to see how big my atoms are. So how would I calculate that? Well, actually, it's kind of easy with the things that we already had. So what I want to know is the spread of the position of an atom. Did I define it this way? Let me do it correctly. Yeah. So I can just define the spread, or the variance if you want, as x. Oh, let me get everything right. Yeah, there we go. So when I say I want to know the size of the atom or how much it's vibrating, what I really want to know is how far away from its center of mass position does it get when I measure it repeatedly, right? Or in other words, what's the variance of the displacement? So this is the definition of the variance, right? And actually the nice thing is, with all of the techniques that we had before the break, you can just calculate this directly. So first of all, this part, you know without doing any calculation. What is the average position of an atom? Or the average displacement, sorry. 0, exactly. Why? Yeah, or if you want, because it's at rest or in thermal equilibrium. So it's not moving, nothing depends on time, so it doesn't displace either. So the average is 0. It's sort of going around its center of mass. So all we need to calculate is this other one. Okay? And then we've already learned how to do this. It's actually straightforward. The first thing you do, as always, is to say that if you want this thing, let's calculate the square of it, right? Because square roots are nasty. So square will get rid of the square root. Then this is really just xj squared. And then, as always, the first thing you do is just take the Fourier transform. Minus I. No. Right, now notice, this time I cannot use my trick of... Wait, I did do something wrong. Oh yeah, there's a k prime as well. Good. This time I cannot use my trick of inventing a delta function and then getting rid of all the sums. Because for the delta function I needed the sum over j, right? And in this case I'm really interested in the variance of the position of one single atom, not of all of them combined. So there is no sum over j and I cannot do a delta function anywhere. But it's okay, it doesn't really matter that much. Because I already know what these operators x are, right? We wrote these operators before in terms of creation and annihilation operators. So let's just do that again. So then this becomes 1 over n, sum over k, k prime, e minus k. Yeah, there it is. Position is something like a dagger plus a. Right? And the prefactor you just look up in the lecture notes. Oh, I should also tell you, in this whole course, don't worry about memorizing formulas and prefactors and stuff like that. If you ever need it in an exam or homework, it will be given. Like you're studying physics, not topology or topography or something. Okay, now let's think about this for a second. Actually, first of all, let's think about the expectation value. You know how to calculate an expectation value, right? You just replace, I mean, these brackets really are brass and cats. And if I want the expectation value in the ground state, I write the ground state out there and I act with A and A dagger on it and I see what happens. But the ground state, of course, any system is only in its ground state at exactly 0 temperature. And although 0 temperature is very interesting, it's not very practical. So really, we're also interested in what happens at finite temperature. So in that case, you would have to replace this expectation value, quantum expectation value, by a thermal expectation value. Do all of you remember how to calculate thermal expectation values? Good. So let me just write it for completeness. Wait. Actually. Yeah, that's the definition of the thermal expectation value if you want. I'm pretty sure you all derived it in statistical physics in third year bachelor, or second year bachelor maybe even. So look it up again if you can't remember it. Or just take this as the definition. This thing on the bottom is called Z, it's the partition function. The thing on the top is the one that you have to always calculate. So the sum over psi is over all of the states of the system. If you happen to know the energy eigenstate of the system, then you can sum over all the energy eigenstates, and then you can immediately see that this is just a sum over Boltzmann vectors times the expectation value of an operator. So it is also what you would expect for a thermal ensemble. Does this look familiar to most of you? Some of you at least? All right, otherwise look up your statistical physics textbook again. All right, so let's use this thermal expectation value in our expression here. But then the thermal expectation value is really just a sum over states, right? And to make this sum doable, we'll use energy eigenstates. Okay, but the system we're thinking about here is a bunch of harmonic oscillators. So what are all of its eigenstates? What's the ground state? Sorry? That's the ground state energy. The ground state itself is just the state without anything excited, right? Without any particles in it or any ladder operator applied. What are the excited states? How do you get an excited state?
Use a ladder operator.
You use a ladder operator, or you create a particle in our new language. But always, you create quantized numbers of particles. So all eigenstates are number states. Right? Eigenstates is the number operator with a well-defined number of particles in it. And even in this thermal ensemble, all of the states that I will sum about are exact number states with an exact number of particles in it. All right? So then, let's think about this expectation value. So, this expectation value, I'll write it here again. Nope. So we are worrying about A dagger K, A minus K. So first of all, let's think about terms that look like this. Oh, without. So these A dagger terms. What are they? What's their value? Sorry? Yeah, so you create two excitations, two particles. What is this expectation value? Zero. Why?
Because
Oh, you're right, I'll tell you.
Because they are want to know.
Yeah? So whatever you do, right, you start here with a state that has n particles in it. Whatever. Actually, n for every value of k. There's just some number of particles. Then you create an extra particle. And you create yet an extra particle. So together, these will have n plus 2 particles in it. But this state is the same as that you began with, because it's a trace, right? Psi and psi, the same on both sides. So then you're really looking at the overlap between n and n plus 2 particles. These are perfectly good eigenstates of the Hamiltonian, so they must be orthonormal, and this must be 0. So the overlap between a state with n particles and n plus 2 is 0. Sorry? Even in the thermal ensemble, because even in the thermal ensemble, see, the thing on the right is the same as the thing on the left. So now you can make it for every term in this sum separately. All of these terms will be 0. I do, because the Hamiltonian is a bunch of harmonic oscillators, so you can always write it like n plus 1/2 times h bar omega. So it's a number operator. It doesn't change the number of particles. This is the crucial thing. Yeah. Yes?
I don't see why we need the thermal expectation because we have the pure quantum state.
Yes, but I could want to study it at finite temperature.
Yeah, but we can also like calculate the expectation, the ordinary expectation using the number of states.
Yes, and you will find the 0 temperature expectation value. Which is fine, it's a useful thing. We will actually discuss it in a second, but it's not all that there is. So I want to be a bit more general. Okay, so all of these things are 0. Basically because, okay, this is maybe too much, but just for fun, what is this? This expectation value? Also 0. Why?
Same reason.
Exactly, good. Also, if I take 2 particles away, I change the number of particles, so the overlap will again be 0. Good. Then let's go for this one.
That's one.
Not quite?
0.
Mm.
Delta between k and k.
There's definitely a delta function. Why is that?
Because you destroy the same number.
Right, if k and k prime are not the same, right, then you would change the number of k prime particles and you would change the number of k particles, and again the overlap is 0. But if k and k prime are the same, that's what we have now, right? Then you get an answer, and what is the answer? Yeah, exactly, it's the thermal expectation value of the number operator, right? It's just the number operator. And now think back to statistical physics. What is the thermal expectation value of the number of bosons in any system? It's exactly the Bose-Einstein distribution, right? So this is Bose-Einstein distribution. You guys remember the Bose-Einstein distribution? It's defined as the thermal expectation value of the number of bosons, given their energy. Oh, no, one final one. It's almost the same. As a 1 minus, right? Because you have to take the commutator for it to be a number operator. So this is going to be, well, there's definitely a delta function, and then 1 minus n, okay. Or plus. Bosons. Okay, so actually with all of these, we can just look back at our big sum here and just plug them in. If you write it out, you get 4 terms, which are exactly these 4 terms. So we already have the answer. Right, and we just write it out. And what we find is the following. Yeah. Yes.
Could you explain why you've got a +1?
On the bottom here?
Yeah, well,
Good. Because a dagger is not a number operator. Right? A dagger A is a number operator. So that's the one I know. I can replace it by Bose-Einstein distribution. So that's the one I want. But A and A dagger don't commute. The commutator of commutator of A dagger is 1. So to make A dagger is A dagger A plus 1. That's that plus 1. And that's actually very important. So it's the same plus 1 that you end up here. This 1 is that same 1. And actually that's very important because now we have two terms here. I'll come back to you in this 1 second. You have two terms contributing to this spread of the wave packet, to this fluctuation, or this vibrating of the atoms. There's one here, which is the Bose-Einstein distribution. And that means, we know what the Bose-Einstein distribution is, right? It's 1 over e to the power omega. Okay. Minus 1. Okay. But the important thing is, there's a temperature in it. Right? So this depends on temperature. As you raise temperature, more and more excitations get occupied. You can understand that, right? Because raising temperature really means adding energy to your system. So this energy gets into bosonic excitations. You just occupy them. But then there's this other part, this 1 here, which does not have a temperature in it. And both of these contribute to the wave packets of the atom spreading out a little bit. So actually, just because one depends on temperature and the other does not, we gave them separate names. The one that depends on temperature, well, it's really about the vibrating of little atoms, right? So you can think of it as if the atom is fluctuating. So these contributions are called thermal fluctuations. But then these other things are not, right? Because they don't depend on temperature. So what are they? Exactly, we call them quantum fluctuations. Actually, the name quantum fluctuations is used for at least 3 different things in physics. This is one of them. It's very confusing always. So it's better not to use the name at all. Also, it's a really bad name, right? Because at 0 temperature, nothing fluctuates. You're just in an eigenstate of the system, and it's stationary. Nothing moves or goes back and forth. These really are not fluctuations. A better name, actually, is quantum corrections. So they're corrections in the sense that if you think about a crystal, you might expect all of its atoms to be localized. But actually, they're not localized. They spread out a little bit. And they do this exactly because these A and A dagger operators don't commute with another. Or, in other words, because they consist of quantum particles. And it's really this quantumness of the particles that spreads out the atoms a little bit and then gives you a correction to your classical expectation. So it's better maybe to think of it as quantum corrections and thermal fluctuations. Is that okay? Okay, so nice. So now we see that actually, okay, if I have a one-dimensional chain of atoms, its atoms actually move a little bit. They spread out, and they do this both because of thermal expectation, because they get heated up a little bit and start shaking and being excited, and simply because they're quantum, and the quantumness broadens their wave function. Now the final question is, how much does it broaden them by? Sorry, you had a question. Let me get back to that first. It's answered. Perfect. Okay. So let me write it down once more. Okay, so first of all, we can replace this number operator by the Bose-Einstein distribution. That we already know. Secondly, we also know something about the energy of the modes. Right, we're interested here in a crystal, but you can go even more generally. Let's say that we're interested just in any system that breaks the symmetry. Then what do we know about the dispersion of the boson modes?
Zero.
It goes to zero at zero wave number, exactly. And that's important here because this sum, well, you see, if the energy goes to zero, then 1 over the energy becomes really large. So those low energy modes will dominate this sum, for sure. So really, we can simplify things a little bit and only consider the modes close to zero. Right? So then you could say this actually is just, it goes like k. Let's say c times k, some constant times k, linear dispersion. Okay? So the fact that we can say that is because of Goldstone's theorem. Now if I replace that by c of k and this other thing by the Bose-Einstein distribution, then I get something that I can actually evaluate. The only other thing I have to do is take the continuum limit and make the sum over k into an integral. But then the integral looks like this. There's a bit of a prefactor which I'll omit. And then integral dk 1 over k.
Sorry,
Yes.
you said that there were some materials which you could not take a linear
Good.
dispersion relation.
Good.
What do you do in those cases?
It's one of the exercises, so you will find out on Monday.
In this case, isn't k supposed to be constant?
It is.
Then how are you taking it?
Good. So the distance between two k values is 2 pi over n. If you take the limit of n to infinity, it becomes continuous. And then I can. So when I take the continuum limit, I really mean consider infinitely many particles. Everything becomes continuous, and I can make the sum into an integral. Actually, at the same time, I've also approximated the Bose-Einstein distribution by some linear till, and I've also gone to polar coordinates, so that k is now only the size of k, the amplitude of k. But all of these steps are in the lecture notes, and I don't want to write them out. But this is the thing you end up with, and this is the important thing. So there are two contributions. This one depends on temperature, that's the thermal contributions. And this one is the quantum fluctuations, or corrections. So, quantum corrections and thermal fluctuations. Now let's look at these integrals. Can you evaluate them? Let's start with the first one, right? The quantum corrections. What is the integral of over k of 1 over k? Yeah, but I'm going to evaluate it, of course, from 0 to something. Infinity. It's ill-defined. Divergent. Right.
And that's regardless of like k maximum.
Yeah, exactly. So it's infinity minus something k maximum.
But sir, that's because 0 is a singularity. If we just increase the limit,
Which limit?
like the lower limit, not 0.
Lower limit? Oh, but why would you? Because Goldstone's theorem tells you that Goldstone's theorem tells you that there are modes arbitrarily close to 0. So you must enclose always to 0. So actually, it just means that these things diverge. But that means that I've been cheating you from the beginning, right? Because what is this thing that becomes infinite? It's the size of an atom, the distance over which it fluctuates. So if I draw my little chain here, I'm drawing something completely ridiculous. Because really this atom here, atom number J, it fluctuates back and forward. Not just a little bit, but by infinity. By itself, regardless of its neighbors. So this is not a very good crystal. What it's really saying is that the crystal in one dimension cannot exist. It's melted already in the ground state. Completely delocalized. We can do a little bit better by going to higher dimensions. So I don't want to do the complete derivation, but if you go through it, basically everything we did also follows in higher dimensions. The only thing that changes is that this d of k becomes, let me write it down correctly. So you get d of k, 1 over k, same thing, but then you get an extra k to the power d minus 1, where d is the dimension. So you see for d is 1 it falls away, we had the result just a second ago. But for d is 2, it's okay. Right? Then you just get a constant. For d is 3, it's actually quite good already. And the higher in dimension you go, the more stable you become. So what this is saying, it diverges in one dimension, but not anything higher. Okay, we can do the same thing for this other function, the thermal expectation value. There's an integral over 1 over k squared. Okay, and again it goes from 0 to something. So what will that tell you? Well, again, it's infinite, right? It has a divergence at 0. Now, if I make it in d dimensions, this becomes k times d minus 1 in just the same way. The k times d minus 1 comes from the Jacobian, by the way, when you go to polar coordinates. It's something that you can easily do yourself. So this one also diverges. But in which dimensions? Right, d equals 1 and d equals 2. So what this is telling you is that at 0 temperature, the second term doesn't exist, at 0 temperature, you cannot have a crystal, or in fact any spontaneously broken symmetry, in 1D. But you can in 2D and 3D at exactly 0 temperature. If you have any temperature at all, I don't care how small it is, right? 10 to the minus 100 Kelvin is enough. Any temperature at all, then the second term will kill your ordered state in 1 and in 2 dimensions. So you cannot have a crystal, no magnet, no superconductor, no ordered state at all, nothing that breaks the symmetry in 1 and 2 dimensions at any finite temperature. They melt as soon as the temperature is larger than 0. Okay, and actually, to derive all of this, we only used one thing. Remember? We used Goldstone's theorem repeatedly. And Goldstone's theorem applies whenever you break a continuous symmetry. So this argument works for anything that continuously breaks a symmetry. So really, we can only have broken symmetries and interesting objects in higher than 2 dimensions. So that, by the way, has then its own name. That's called the Mermin-Wagner theorem. One second. So what it's telling you is that it's, you're lucky to live in 3 dimensions. Because in 2 you wouldn't exist, you would be spread out all over the universe. In 1 you definitely would be, even at 0 temperature. And in fact, as we go on in the coming weeks, you'll learn that you're even luckier, because in 4 and higher dimensions, nothing works anymore. There's no dynamics, you can only be in one fixed state and you will never move. So really 3 dimensions is the only number of dimensions in which any type of interesting life could happen. Well, and luckily here we are. All right, but all of this is general, right? That's the point. Yes, go for it. Good. Yes. So graphene is a 2-dimensional material. In fact, we had these carbon nanotubes on the slide a second ago, or yesterday, which were 1-dimensional materials. So apparently 1 and 2-dimensional materials do exist in reality. In fact, when graphene was first discovered, it was hugely controversial. And people said that this must be a cheat, because obviously graphene cannot exist, right? Because it's 2-dimensional. It would be destroyed by Mermin-Wagner theorem. Yet it's now, everybody makes it, every lab in the world. You can just look at it. So, what breaks down? How do we get around the Mermin-Wagner theorem? Good, of course you have to look at where the ingredients break down, right? And we use Goldstone's theorem. So one thing could be that there are long-distance forces, but it happens that graphene is actually quite good at screening forces, so that's not it. It could have a discontinuous symmetry, but translational symmetry is continuous, so that also is not it. Sorry?
The boundary is not periodic.
The boundary is not periodic. That makes a small effect, but actually just a small one. Sorry?
It's not truly dimensional.
It's not truly what?
It's not truly two-dimensional.
Ah, very good.
And the universe.
Exactly. Good. So it's not two-dimensional in at least two different ways. First of all, if you really have graphene, it ripples always. So it's not quite two-dimensional, right? You really need to embed it in 3 dimensions to see that. And these ripples are enough to make it a bit more two-dimensional than what we're doing here. Secondly, you never have a piece of graphene hanging in the middle of the universe without anybody looking at it. It's always there on a table or a substrate or clamped or whatever. So it's actually connected to the 3-dimensional world. So if you think about graphene plus everything around it, that's a 3-dimensional object. And together they can break a symmetry. There's one more. Actually, that comes back to almost to your non-periodic boundary conditions. Any piece of graphene that you see in the lab is also finite. Right? It has a size, a maximum length. Because it's finite, actually, okay, in principle it should still spread out. You know, even if we could completely flatten it and put it in the middle of the universe, it should spread out over all of space. But the time scale that you need for it to spread out is inversely proportional to the length. No, it's proportional. Yes, inversely proportional to the length. Right? So for a small thing, actually, it can exist for quite a long time before it spreads out completely. So there are 3 reasons that you can still see graphene. That's the short answer. And that's also a good lesson, right? That, I will teach you a lot of general things, and you should always question whether these general things have any applicability at all. But of course, it's good that they exist, or good to know that they exist, because then you can think of why graphene really is so special. And that will teach you new things about graphene. All right, one last.
Does graphene actually spread in a trivial way?
Oh, very slowly. But unmeasurably slowly. Yeah, but it's not a limit that we can ever achieve. Yeah. But in principle, yes.
So, don't really exist so-called 2D.
Exactly. So exactly. So 2D you should always take with a grain of salt. It's always at least 2D in a 3-dimensional world because we live in a 3-dimensional world, and you cannot shield something completely from its surroundings. So it's always a little bit 3D. All right. Well, that was 2 major theorems of physics that we learned in 1 hour. So digest it, and then tomorrow we'll switch to phase transitions.